So the simplest bonding theory is known as the Lewis theory. This bonding theory shows how atoms are connected or bonded together in order to form molecules. The Lewis structure illustrates the bonding between specific atoms involving their valence electrons. When drawing the Lewis dot structures, be mindful of these three main things: the number of valence electrons, the octet rule, or rule of 8 electrons around a central atom, and the fact that hydrogens only form one bond. There's a lot of different ways or methods in drawing Lewis structures, and here's one of them. The first step is to arrange the atoms next to each other that you think are bonded together. The majority of organic molecules have structures in which hydrogens and halogens are placed as terminal atoms, meaning the outside atoms. So in methyl chloride, for example, CH3Cl, carbon is the central atom, and the rest are terminal atoms. These specific terminal atoms can only form one single bond. In CH5N, the hydrogens are terminal atoms, and both carbon and nitrogen are the central atoms. In this example, the carbon forms 4 bonds, and the nitrogen forms 3 bonds. The next step is to count the molecule's total number of valence electrons. If it's an anion, make sure to add 1 electron for each negative charge. And if it's a cation, subtract 1 electron for each positive charge. Then, arrange the electrons around the atoms, place a single bond between every 2 atoms, which consist of a pair of electrons, and make sure that every single atom is following the octet rule, except for row 1 elements, including beryllium and boron. Form multiple bonds like double or triple bonds, and finally, assign formal charges to all atoms to determine the most stable structure. We'll look at formal charges in the next few slides. So here's problem 1.4. Draw a valid Lewis structure for each compound. So the first one here is ethane, CH3CH3. So the first thing that you want to do here is to arrange the atoms, the elements. So we're going to have the central atom and the terminal atoms. And we know that hydrogens are always the terminal atoms. So we have carbon as the central atoms, and then we're going to surround them with the terminal atoms. And there's a total of 6 hydrogens. So as you can see, carbon has to form a total of 4 bonds. Each carbon atom needs to form 4 bonds in order to follow the octet rule. Hydrogen is one of the exceptions because it only contains a single electron. So it's stable just by having a single bond. So we're going to form 1 bond for each atom, including carbon. So now you can double check for the octet rule to make sure that each atom follows the octet rule. So this carbon has 4 bonds, so it has 8 valence electrons. This carbon has 4 bonds as well, so it follows the octet rule. Next one here is CH5N. So again, we're going to arrange the atoms, and both carbon and nitrogen are going to be central atoms. And then we're going to arrange the terminal atoms outside, surrounding the central atoms. And then we know that carbon has to form a total of 4 bonds, so we can go ahead and draw a line, a single bond to each hydrogen atom, because we know that hydrogens can only form a single bond. So we'll do the same thing for this hydrogen right here and this 5th hydrogen. And then carbon will form a single bond with the nitrogen. So now you can see that the central carbon atom has a total of 8 valence electrons, following the octet rule. So you have 2, 4, 6, and 8. Nitrogen, on the other hand, only has 3 bonds, which means that it has a total of 6 electrons. And so it doesn't satisfy the octet rule. So what that means is that we're going to have to add a lone pair of electrons in order to satisfy the octet rule. So by adding a pair of electrons here gives nitrogen a total of 8 valence electrons. So 2, 4, 6, 8. So this is the Lewis dot structure for this compound. And the third one here is C2H5Br. So again, we're going to set the 2 carbon atoms as the central atom. And then we're going to surround it with the terminal atoms. So both hydrogens and the halogens will always be central atoms. Terminal atoms. So we have hydrogen here, here, and here surrounding carbon. And then we'll do the same thing for the second carbon, and then finally bromine. So all the hydrogen atoms and bromine will be central atoms. And then we're going to start connecting the atoms by forming a bond. So here's a single bond here, 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 making sure that they have a total of 8 valence electrons. So now when you look at carbon, it has 2, 4, 6, 8. The second carbon also has 8 valence electrons, 2, 4, 6, 8. And then bromine only has 2 electrons. And so in order for this to have a total of 8 electrons, we're going to include lone pairs of electrons. And so when you recount the total of electrons for bromine, you have 2, 4, 6, and 8. And if an atom doesn't have a full octet, then form multiple bonds as necessary. The simplest way to form an octet is to convert a non-bonding lone pair into a bonding pair. So when you look at this structure on the left, we have a lone pair on the carbon, and this carbon has a total of 8 valence electrons, following the octet rule. On the other hand, this carbon only has 3 bonds, which means it has 6 electrons, not satisfying the octet rule. And so by moving this lone pair and sharing it with the other carbon that lacks 2 electrons, forms multiple bonds, which is basically a double bond. So again, all we did is we changed one lone pair into a bonding pair between the 2 carbon atoms. Alright, now let's look at problem 1.6. Draw an acceptable Lewis structure for each compound, assuming the atoms are connected as arranged. Alright, so we're going to look at the first one here, which is hydrogen cyanide, HCN. And so the first thing that we want to do is draw a line between hydrogen and carbon, because we know that hydrogen can only form a single bond. And then carbon lacks 3 more bonds, and so we can just draw 3 lines connecting carbon and nitrogen. So as you can see, carbon now satisfies the octet rule with a total of 4 bonds. Nitrogen, on the other hand, only has 3 bonds, which lacks another lone pair of electrons. So all we have to do is add a lone pair of electrons outside nitrogen, and this is the Lewis structure for hydrogen cyanide. For the second example here, we have C3H4 arranged in this format here. So we have the carbon atoms that are lined up, connected to each other, and the hydrogen atoms. So again, because hydrogen only forms a single bond, we can go ahead and connect the hydrogens with the carbon. And then we know that each carbon atom should have a total of 4 bonds for a total of 8 bonding electrons. So we have 1 bond here, and then 3 bonds here between these 2 carbon atoms. And so now when you look at each carbon atom, they satisfy the octet rule. So this carbon has 1, 2, 3, 4 bonds. This carbon also has 1, 2, 3, 4 bonds. And finally, the third carbon also has 4 bonds, sorry. A total of 4 bonds. So each carbon satisfies the octet rule. So the formal charge of an atom in a given molecule is defined as the charge that specific atom would have if the electronegativity effects were ignored. And it can be calculated using this formula shown here. So we have the formal charge, which is equivalent to the number of valence electrons of that atom minus the number of electrons that atom owns. The number of electrons that an atom owns is basically all of its unshared electrons plus half its shared electrons. Let's look at a few examples in the next slide. So here's a few examples on how to determine the number of electrons owned by an atom. Looking at this carbon on the left, you can see that it has a total of 4 bonding pairs, which equates to a total of 8 bonding electrons. Half of that is owned by this carbon, which is equivalent to 4 electrons. This carbon on the right has 3 bonding pairs, which is equivalent to 6 bonding electrons. Divide that by 2 and you get 3 plus the lone pair of electrons. So that's a total of 5 electrons owned by this carbon. These 2 carbons at the bottom are the same because they both have a double bond and 2 single bonds. So that means that this carbon on the left has a total of 8 bonding electrons, and so half of that is 4. So each carbon atom owns 4 electrons. So here's problems 1.7 and 1.8. So the first problem here is calculate the formal charge on each second row atom. So the first thing that you want to do here is to determine the second row atoms. So we have, for the first one, nitrogen. What would be the formal charge on this atom? So the first thing that you want to do is count the total number of valence electrons for that atom. So in this case, we have 5. And then we're going to subtract the number of electrons owned by nitrogen in this structure. So it has a total of 4 bonding pairs. So half of that is owned by nitrogen. So 4 bonding electrons or 4 bonding pairs equates to 8 bonding electrons. So divided by 2 and you get 4. So 5 minus 4 equals positive 1. So the formal charge on that nitrogen is positive 1. What about this carbon right here? Because this is also a second row atom. So this carbon has 3 other bonds because it's bonded to 3 hydrogen atoms, plus another bond with the nitrogen. So that's a total of 4 bonding pairs, which equate to 8 bonding electrons divided by 2, 4 electrons owned. And so this carbon has 4 valence electrons minus 4 owned electrons, which is equivalent to 0. So this carbon has a 0 formal charge. What about this nitrogen right here? Nitrogen has 5 valence electrons, and then we're going to subtract the total number of electrons owned. So 4 bonding pairs, that's 4 electrons. So it has a positive 1 charge. And this carbon right here owns a total of 1, 2, 3, 4, 5 electrons. So 4 valence electrons minus 5 owned equals minus 1. So again, this nitrogen has a positive 1 charge. This carbon has a negative 1 charge. What about ozone? O3. So let's look at this oxygen right here. It has 6 valence electrons. And then we're going to subtract the number of electrons owned. In this case, we have 1, 2, plus 4, 6. So that's equivalent to 0 formal charge. This oxygen right here also has 6 valence electrons minus 1, 2, 3, 4, 5 owned. Positive 1 charge. And finally, this one right here has 6 valence electrons minus a total of 7 electrons owned. So that's minus 1. And the last example here, let's look at, so this carbon is basically the same as this carbon right here, which would have a 0 formal charge. This oxygen right here is the same as this oxygen with a double bond, and the formal charge is also 0. So again, we can calculate that. We have 6 valence electrons minus 6 electrons owned, which is equivalent to 0. This oxygen right here has 6 valence electrons minus 7 electrons owned. That's minus 1. And finally, this nitrogen right here has 5 valence electrons minus 4 electrons owned, which gives it a positive 1 charge. Problem 1.8, draw a Lewis structure for each ion. So now we have Now we're combining Lewis structure with formal charge. So the first thing that you want to do here is to arrange the elements. And so I want the carbon to be my central atom. And then I'm going to surround it with terminal atoms. And then the carbon will have 4 bonds, and each hydrogen atom will have a single bond. All right, so here's 4 bonds. And then, as you can see, carbon now has a total of 8 electrons, following the octet rule. Oxygen doesn't. By adding 3 lone pairs around it, that will satisfy the octet rule. And so we have 1 pair, 2nd pair, and 3rd pair. And then we have to apply formal charge. Carbon has 4 valence electrons, and subtract the number of electrons owned, which in this case is 0. So that carbon has 0 formal charge. This oxygen, on the other hand, would have a negative charge because of the fact that it has 6 valence electrons minus 7 owned electrons. So that's -1. All right, what about CH2 with a negative charge? So again, HC2 with a negative charge. So you have 2 carbon atoms, and so I'm going to connect them together, and then 1 hydrogen next to one of the carbons. So each carbon has to have a total of 4 bonds. So I'm going to connect one single bond here between hydrogen and carbon, and then 3 bonds between the 2 carbon atoms. So this carbon on the left satisfies the octet rule with a total of 8 valence electrons. This carbon on the right only has 6 bonding electrons, and so adding a lone pair next to it would satisfy the octet rule. And then apply the formal charge. This carbon, again, owns 4 electrons, and so 4 valence minus 4 owned electrons equals 0, so it has 0 formal charge. This carbon on the right, on the other hand, will have a -1 formal charge. So again, 4 minus a total of 5 owned electrons. And the third one here is CH3NH3. So both carbon and nitrogen will be the central atom. So we're just going to connect them together and with a single bond, and then we're going to surround the central atoms with the hydrogens, a total of 6 hydrogens. All right, so I'm going to connect one single bond for each hydrogen, and then we're going to take a look at the octet rule and see if the octet rule is satisfied for both atoms. So this carbon has a total of 8 valence electrons, so it satisfies the octet rule. This nitrogen, same thing. And now we can apply the formal charge. So again, this carbon having 4 bonds will have 0 charge. This nitrogen having 4 bonds will have a +1 charge because of the fact that it owns a total of 4 electrons with 5 valence electrons. So 5 minus 4 equals 1. So it has a positive formal charge. And finally, we have CH3NH with a negative charge. And so carbon and nitrogen again will be the central atoms. And then we're going to connect, or we're going to draw the hydrogens around the central atoms. And then we're going to start connecting single bonds for the hydrogens. Looking at this carbon, if we connect another bond between carbon and nitrogen, that will satisfy the octet rule. This nitrogen right here only has a total of 4 bonding electrons, and so it lacks 4 more electrons, and we can just turn that into lone pairs. So now this nitrogen has 8 electrons, so 2, 4, 6, and 8, and then apply the formal charges. This carbon has 4 bonds, and so it will have 0 charge. This nitrogen, on the other hand, owns a total of 6 electrons. So 5 minus 6 equals -1. So this is negative charge. All right. So that's how you draw Lewis dot structures and applying formal charge. So here's a table showing you the typical formal charge for carbon, nitrogen, and oxygen. The first carbon here owns 3 electrons, and subtract that from its number of valence electrons and you get positive 1 formal charge. This nitrogen here on the left has a positive 1 charge, and that's because you subtract 4 owned electrons from its 5 valence electrons, so you get plus 1. And oxygen right here on the left has a positive 1 charge because of the fact that it has 5 owned electrons, and you subtract that from 6 valence electrons and you get positive 1. Many organic molecules with the same exact chemical formula can have multiple possible Lewis structures. These compounds are called isomers. An example is shown here. Both ethanol and dimethyl ether have the same exact chemical formula, C2H6O, but their Lewis structures, as you can see, are completely different because at least one of the atoms is connected or bonded differently. Since their structures are different, isomers are different compounds with completely different physical and chemical properties. There are 2 different types of isomers, constitutional isomers and stereoisomers. Constitutional isomers are molecules with the same formula, but the atoms are connected differently. Stereoisomers, on the other hand, are molecules with the same formula and atomic arrangement, but the atoms are oriented in space differently. This type of isomer will be discussed in greater detail in Chapter 5. So here's practice problem number 10. Draw the Lewis structures for each molecular formula. So the first one here is C2H4Cl2, and it tells us that it has 2 isomers. So can we draw these 2 isomers? So our focus here will be on constitutional isomers, which again are defined as molecules with the same exact chemical formula but different atomic arrangement. Okay, so let's take a look. So C2H4Cl2, so we're going to connect both carbon atoms because these are generally the central atoms. And then we're going to surround them with the terminal atoms. So we have hydrogen here. There's a total of 4 hydrogens. And then 2 chlorines. All right. And so earlier you learned that hydrogens can only form a single bond, and halogens technically can only form single bonds as well. And so we're just going to connect single bonds here. And this is one isomer of this molecule with this specific chemical formula. What would be the other isomer? So again, constitutional isomer is when some of the atoms are connected differently. And so with this example, we have both chlorine atoms that are bonded to the second carbon. So if this is your first carbon here, then this is the second carbon. So one other isomer would be one in which the 2 chlorine atoms are bonded to 2 different carbons. And so we're going to put chlorine on one carbon and then leave the other chlorine on the second carbon. So now we have a hydrogen here, and then a chlorine on the first carbon, and then another chlorine on the second carbon. So we basically switched the chlorine and the hydrogen here. So these are the 2 isomers for this compound. Now let's look at C3H8O. So it says that we have 3 isomers for this compound. Generally, the larger the number of carbons, the more isomers there are. So we have 3 carbons, so we're just going to connect 3 carbons, 1, 2, and 3. And then we're going to distribute the terminal atoms. So 1, 2, 3, 4, 5, 6, 7, and 8. So I'm going to put oxygen as the um, sort of like a bridge between carbon and hydrogen. So the 8th hydrogen will be over here. All right, and so now we have this oxygen that's bonded to this carbon, and then this hydrogen is bonded to this hydrogen, this oxygen here. And so each hydrogen atom will have a single bond. And so now this oxygen atom here only has 4 bonding electrons. And so if you put lone pairs here, then what we have is one of the isomers of this compound. So now one other constitutional isomer of this would be to put oxygen, or this OH group right here, bonded to the middle carbon. So we're going to switch it around. So we have carbon, 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 and then oxygen, hydrogen right over here. All right, and the rest would be hydrogens. So now we have 2 different compounds which are isomers, constitutional isomers. And the last isomer would be to replace one of the carbons, maybe the middle carbon, with an oxygen. So now we have carbon, oxygen, carbon, and then another carbon here. And then a total of 8 hydrogens. So we have 1, 2, 3, 4, 5, 6, 7, and 8. And this oxygen will have 2 lone pairs as well. All right, so what we have here is another isomer of this compound. So all 3 compounds are isomers of one another, specifically constitutional isomers. And for the last one here, we have C3H6. Again, we're just going to connect the carbon atoms 1, 2, and 3. And then since we only have 6 hydrogens to give, I'm going to equally distribute this among the 3 carbon atoms. So we have 1, 2, 3, 4, 5, and 6. All right, so we're going to form a bond here, here, and here. So if I put a double bond here, then this carbon right here will have more than 8 valence electrons. So what we can do is I'm going to move this hydrogen onto the left-hand side, and then for a bond between the carbon and the hydrogen. So now each of the carbon atoms has a full octet. So you can see that you have this carbon with 4 bonds, the second carbon also with 4 bonds, and then the third carbon having a full octet or 4 bonds. So what would be the second isomer? So this one is going to be a little bit different, and you can't just move the double bond on the left hand side because that's actually going to look like this molecule as well. You're just flipping it over, and so that wouldn't count as an isomer. What we can do is we can form a ring structure, and you're going to learn more about ring structures later on. But if you have a carbon here, here, and here, that's a total of 3 carbon atoms bonded together, forming a ring structure, and each carbon is bonded to 2 hydrogen atoms. All right, so these are the 2 isomers for C3H6. Whenever you're drawing the Lewis dot structures, just always remember that there are elements that don't normally follow the octet rule. These elements can have a stable bond having either an incomplete octet or an expanded octet. Elements like beryllium, hydrogen, and boron can be stable with an incomplete octet. Similarly, elements in the 3rd row and beyond can have an expanded octet and still be considered stable. Both sulfur and phosphorus in some Lewis structures can have more than 8 bonding electrons. Beryllium, for example, only has 2 bonding pairs, which equates to 4 bonding electrons, Boron, on the other hand, has a total of 3 bonding pairs, which is equivalent to 6 bonding electrons. Yet these molecules are considered stable. Here we have the Lewis dot structure for dimethyl sulfoxide, or DMSO, and as you can see, the sulfur atom has a total of 4 bonding pairs and 1 lone pair for a total of 10 electrons, which disobeys the octet rule. Looking at sulfuric acid, this is the Lewis dot structure for sulfuric acid. The sulfur has a total of 12 electrons. Sulfur has a total of 6 bonding pairs, which is equivalent to 12 electrons. Both phosphorus atoms in alendronic acid contains a total of 10 electrons. And the reason why these elements on the third row and below can accommodate more than 8 electrons is because of the fact that they can access the d orbitals. Some molecules, such as those with formal charges and or with double and triple bonds, can have Lewis structures that can be represented in several different ways. This structure shown here on the left, for example, can also be represented by this structure on the right. These structures are known as resonance structures because the molecule itself can resonate between these two structures. The only difference between the two is the arrangement of the electrons. In this example, the structure on the left has the double bond between the carbon and the oxygen, and the formal negative charge on the nitrogen. But the structure on the right has the double bond between the carbon and the nitrogen with the formal charge on the oxygen. The real structure of this molecule, however, is a combination of the two, known as a resonance hybrid, which basically shows the characteristics of both structures. This resonance allows certain electron pairs to be delocalized over 2 or more atoms, which adds molecular stability. Hence, a molecule with multiple resonance forms is said to be resonance stabilized. Here's a few important principles that you should always remember regarding resonance structures. Only the hybrid structure can accurately represent the structure of a molecule or ion. Resonance structures are not in equilibrium with each other. And finally, resonance structures are not isomers. Two isomers differ in the arrangement of both atoms and electrons, whereas resonance structures differ only in the arrangement of electrons. Here's practice problem number 11. Classify each pair of compounds as isomers or resonance structures. So first, let's differentiate isomers from resonance structures. We know that resonance structures are structures with different electronic arrangement, the arrangement of the electrons. For isomers, you have structures that are different in atomic arrangement and electronic arrangement. So when we look at the first problem here, you can see that this carbon is the central atom, whereas in the other structure, the nitrogen is the central atom. So you can see that they are different in atomic structure. And so these two structures are considered isomers. The second problem here, we have all the atoms that are in the same spot, the same location. The only thing that's different between the two structures is the location of the double bond, right? So with this structure, the double bond is connected to this oxygen on top, whereas on the second structure, it's in another oxygen. And so because these two have the same atomic arrangement but different electronic arrangement, these two are resonance structures. Let's look at practice problem number 12. Considering structures A through D, classify each pair of compounds as isomers, resonance structures, or neither. So for A and B, what is the relationship between these two structures? So the very first thing that I would look at is the atomic arrangement. Are the atoms in the same locations? So for A and B, we have CH3, carbon, carbon, oxygen. So it looks like all the atoms here are in the same location. So these two structures could be resonance structures, because the only difference is the location of the double bond, right? So you have the double bond up top and the double bond here at the bottom. And so I would say that A and B are resonance structures. All right, what about A and C? So when you look at A and C, you have a CH3 here, a CH3 here, carbon double bonded to an oxygen. This one is carbon single bonded to an oxygen with a hydrogen over here. And so do they have the same number of atoms? This structure C here has an extra hydrogen, right? So you have a total of 4 hydrogens in structure A, but a total of 5 hydrogens in structure C. And so A and C are completely different structures, different atomic arrangement, different electronic arrangement, and won't even count as an isomer because of that extra hydrogen in its structure. So A and C are considered neither resonance or an isomer. All right, what about A and D? So when you look at D here, do they have the same atomic arrangement? Not really, because you have CH3 here and no CH3 anywhere. And so this would not count as a resonance. But what about the position of the atoms? So we have, or the number of the elements. So hydrogens, we have 4 hydrogens here and also 4 hydrogens over here. 2 carbons and 2 oxygens on both structures, and so I would say that the only difference here is the bonding, the atomic arrangement, basically. And so this would count as isomers, constitutional isomers. So A and D would count as isomers. All right, what about B and D here? So we have CH3. Okay, so looks like the atomic arrangement might be different. We have a total of 4 hydrogens, 2 carbons, and 2 oxygens. And so we have same number of lone pairs, 1, 2, 3, 4 lone pairs. This one, 1, 2, 3, 4 lone pairs. So B and D are also isomers. So how do we draw resonance structures? The first step is to draw one Lewis structure of the molecule or ion, and then locate the position of the atoms, the lone pairs of electrons, as well as any double or triple bonds. The reason why is because the atomic arrangement does not change. The only thing that's changing is the location of the electrons. It could be a bonding electron or lone pairs of electrons. So this brings us to rule number 1. 2 resonance structures differ in the position of multiple bonds and non-bonded electrons. The placement of atoms and single bonds always stays the same. The second rule that you need to remember is that 2 resonance structures must have the same number of unpaired electrons. So when you look at structure A, you can see that there are no unpaired electrons anywhere in the structure. But in C, this would be incorrect because you have 2 unpaired electrons, one in the carbon and one in the oxygen. Rule number 3 says resonance structures must be valid Lewis structures. Hydrogen must have 2 electrons and no second row element can have more than 8 electrons. So when you look at this structure right here, this would be an invalid Lewis structure because of the fact that this carbon has a total of 10 electrons, which violates the octet rule. So when you count the total number of electrons, you have 1, 2, 3, 4, 5 bonding pairs, which equates to 10 electrons. Curved arrow notation is extremely important in organic chemistry because it shows you the movement of an electron pair. Here's a few examples. In this structure, you have 3 different carbons. You have the first carbon that's double bonded to the second carbon, and this second carbon is single bonded to a carbon with a positive charge. So this tells you that this third carbon here with a positive charge is electron deficient. So that means that one of the bonding electron pair here in the double bond can move and transfer to this carbon, forming a bond between the second carbon and the third carbon. And the positive charge is then transferred to the first carbon, as shown here in this structure. In the second example, we have the first carbon with a lone pair, and this carbon is bonded to a second carbon that's double bonded to an oxygen. So the movement of electrons here happen at the same time. So when the lone pair turns into a bonding pair, this bonding pair between carbon and oxygen will break and will form into a lone pair that will go on to the oxygen. So what you have is a negative charge on the carbon, and once the electrons were moved, then the negative charge goes on to the oxygen. Some resonance structures, however, can have an incomplete octet. This is the structure of acetone, and as you can see, moving this pair of bonding electrons to the oxygen results in the formation of a positive charge on the carbon and a negative charge on the oxygen, as shown here. Looking at this carbon in structure B, it only has a total of 6 electrons, but this counts as a valid resonance structure. However, resonance structures can never have a second row element with more than 8 electrons. For example, this structure here, structure C, has a negative charge on the carbon and a triple bond with an oxygen. This carbon right here has a total of 10 electrons, which basically disobeys the octet rule. So this is not considered a valid resonance structure. Another thing that you should remember is that when a lone pair is located on an atom that's bonded to another atom with a double bond, a resonance structure is possible. Here's an example. So we have a lone pair on a carbon, and this carbon is single bonded to a carbon that contains a double bond. That must mean that a resonance structure is possible. So when you turn this lone pair into a bonding pair, you can have a double bonded carbon. And when that happens, this double bond here will break and will turn into a single bond, and the 2 electrons will go towards the oxygen, rendering it a negative charge, as shown here. So now you have the negative charge on the oxygen instead of the carbon atom. So let's take a look at practice problem number 13. Follow the curved arrows to draw a second resonance structure for each species. So a resonance structure has the same atomic arrangement. So we can go ahead and draw the Lewis structure with the same atomic positions. So we have carbon, oxygen here, hydrogen, and hydrogen. And it tells us that a pair of bonding electrons will turn into a lone pair. And so you're going to break that, and then you're going to put 2 non-bonding electrons onto the oxygen. And this will generate a negative charge on the oxygen and a positive charge on the carbon. So this is a resonance structure for this molecule. So again, you can follow the formal charge rule, or the concept of formal charge, to determine the charge on these 2 atoms. All right, what about B? Again, same thing. The atomic positions will remain the same. So we have CH3 carbon here, here, and here. And then we have the hydrogens bonded here and 2 here. So the arrows this arrow right here tells us that the lone pair will form a bonding pair between these 2 carbons, forming a double bond. So now we have a double bond here. This one is a single bond here. And then the double bond will break and the 2 electrons will move to the carbon. So we'll have a single bond here and then 2 electrons on that carbon. So now with the formal charge, this will have a negative charge here. All right, that's basically it. All right, what about practice problem number 14? It says use curved arrow notation to show how the first resonance structure can be converted to the second. So the first thing that you want to do here is to look at where the double bonds are. So you can see that there was a double bond, there's a double bond here, and then now the double bond is on the first two carbons. And so in that case, the bonding or the movement of the electrons comes from here to here. All right, and then for the second example here, we have the double bond with the second oxygen, and now the double bond is on the third oxygen on the right. So that means that the bonding electrons moved from here to here. And that's it. And here's another practice problem, number 15. Draw a second resonance structure for each species in A, B, and C, and then draw two additional resonance structures for the ion in part D. All right, so the first thing that I would want to do here is to draw the structure with the same atomic arrangement. Okay, so we have CH3 and then carbon, 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 CH3, hydrogen here, and single bond here. And so what we can do, and then we also have a single bond here, is to basically, so we know that this is electron deficient because of the positive charge. So that means that a bonding pair from the double bond can move to this side of the carbon. And so this goes over here. So now we have a single bond here and a double bond here. And this renders this carbon a positive charge. All right, so that's part A. And then what about for part B? So you have a double bond, a single bond here, and then chlorine with 3 lone pairs. So one of the lone pairs from the chlorine can form another bond with this carbon. So let's just draw an arrow here. Let's try it again. And so once that forms another bond, then the double bond here will break, and the 2 electrons will go to this carbon. All right, so what we have now would be carbon, single bond, carbon, and then a double bond to this chlorine. And then hydrogen is still here, hydrogen here, here, and the only difference is 2 electrons here, a lone pair. And so what that means is this chlorine would now have a positive charge using the formal charge concept. And then this carbon will gain a negative charge. All right, and what about C? So again, we'll draw the location of the atoms here. Okay, and so when you look at this double bond right here, it can, so you see that there's a double bond here, and then a single bond here, and a bunch of lone pairs. So one of the lone pairs of this oxygen can form a double bond with this carbon. So now you have a double bond here, and 2 lone pairs, and this bond here between these 2 atoms will break and will turn into a lone pair, and it will go towards the oxygen. So now you have 1, 2, 3, 4, 5, 6, a negative charge here. And forget about the positive charge here. And that's it. This is one of the resonance structures for this molecule, or for this ion. And for D, it says draw 2 resonance structures, 2 additional structures for ion D, part D. So this one. So this one's a little bit simpler. So the lone pair here can form a bond with this carbon or form with this carbon on the left. All right, so what that looks like would look something like this. So CH3 carbon, double bond here, double bond here. Let's try that again. So you have a CH3 carbon, and then if the double bond forms here, then the carbon and oxygen will only have a single bond. And then that oxygen will gain a negative charge. And then hydrogen here. That's supposed to be a carbon. And then double bonded oxygen and CH3. There you go. And then the second resonance structure would be, let's see, a double bond here and then a single bond here instead. So it would be the reverse. So you have a double bond here and a single bond here instead of this. And those are resonance structures. So now that you know more about resonance structures, let's focus more on the resonance hybrid structure, which is basically a combination of all the possible resonance structures of a given molecule or polyatomic ion. Remember that in this hybrid structure, the electron pairs are delocalized between specific atoms within that structure. Between two resonance structures, the hybrid looks more like the better resonance structure, which is technically the more stable structure. And when it comes to structure stability, you have to have the knowledge regarding formal charges. So how do we know which one is the more stable structure? Well, the structure with more bonds and minimized formal charges is typically the more stable structure. So the more stable structure is the better structure, and this is known as the major contributor. And the resonance hybrid structure looks more like the major contributor. The less stable structure is known as the minor contributor. In this example here, the structure on the left, this structure on the left right here is the major contributor because of the fact that it contains more bonds and fewer charges. The structure on the right is the minor contributor because it has less number of bonds because it only has 3 and more charges. You have a negative charge on the oxygen and a positive charge on the carbon. So that means that the resonance hybrid structure looks more like the major contributor, which is shown here. When two resonance structures are equally stable, which is the case here, the resonance hybrid is essentially the combination of both structures. In this example shown here, both structures are equally stable because the formal charges are minimized. So the resonance hybrid would have a partial negative on both the oxygen and the nitrogen because of the fact that the electrons are delocalized between these two atoms. Here's practice problem number 16. Label the resonance structures in each pair as major, minor, or equal contributors to the hybrid. Then draw the hybrid. All right, so we have two resonance structures here, and we have to figure out which one is the major and minor contributors. So looking at these structures, the major contributor has more bonds and fewer charges. So when we look at this structure on the left, it has 1, 2, 3, 4, 5 bonds. whereas the one on the right has 1, 2, 3, 4, 5, 6 bonds. And so this structure on the right will be the major contributor, and the one on the left will be the minor contributor. So this is major, and this is the minor contributor. All right, what about for B? So for B, we have 1, 2, 3, 4, 5, 6, 7, 8 bonds, and the one on the right has 1, 2, 3, 4, 5, 6, 7, 8 bonds as well. And so now what we need to look at is the charges. Which one has a fewer number of charge? Well, they both have negative charges, and so that must mean that these two resonance structures are equal contributors. And so the hybrid would basically be a combination of both. So when you draw the resonance hybrid structure, it would look something like this. So you have 3 carbons, and you have hydrogens connected to the carbons. And then you have single bonds here. And so what you're going to do is you're going to draw a dashed bond, because it's basically a partial bond. All right, and what about the charges? So both carbons, in this case, this carbon right here, the third carbon and the first carbon, will have a partial negative charge. All right, and that's basically it for practice problem number 16. All right, so now let's look at practice problem number 17. Draw a second resonance structure for A, and why can't a second resonance structure be drawn for B? All right, so let's look at A first. We're going to draw a second resonance structure here. And so the first step would be to draw the skeleton, basically. Okay, so the atomic arrangement remains the same. And then so we have CH3 here, CH3, and then single bonded carbons. And then single bonded hydrogen here. And then a single bond here. So when you look at this lone pair on the nitrogen atom, this can form a double bond with this carbon. And so we can draw an arrow, a curved arrow notation, to indicate that the two electrons, the lone pair of electrons, will form a double bond with this carbon. All right, and then because this formed a double bond, the double bond between the two carbons will break, and then the lone pair will go towards this carbon. All right, so you put a lone pair here on this carbon, and this carbon will gain a negative charge. And again, you can use the formal charge equation or formula. So this carbon owns a total of 5 electrons, and carbon has 4 valence electrons, so 4 minus 5 is negative 1. And then this nitrogen now will gain a positive formal charge. So this nitrogen owns 1, 2, 3, 4 bonds, or 4 electrons, and nitrogen has 5 valence electrons. So 5 minus 4 equals positive 1, and so we will gain a positive charge. So this is the second resonance structure for this molecule. All right, so how do we explain why structure B cannot have a resonance structure or a second resonance structure? Well, let's take a look. So we know that a positively charged atom is electron deficient. And so if one of these bonding pair goes onto this bond here to form a bond, then what you have is a double bond with a nitrogen, and then this nitrogen has 3 hydrogens. So when you look at the nitrogen, it now has 1, 2, 3, 4, 5 bonding pairs. which violates the octet rule. And the only elements that can have more than eight bonding electrons are the elements on the third row and below, and nitrogen is not one of them. And so this violates the octet rule, and so no resonance structure for this molecule.